torus is the surface at the center of this video. Our aim is to construct it as an explicit subset of Euclidean space and prove directly that it is a smooth manifold. We write the torus down as a concrete subset of Euclidean space and verify that it satisfies every axiom of a smooth manifold. There is a concrete reason to avoid gluing. The standard construction takes the plane and declares 2 points equivalent whenever they differ by an integer vector, collapsing r squared onto the quotient r squared modulo z squared. That construction is valid, but it buries the torus inside equivalence classes before we've checked a single topological property. Our goal instead is to write the torus down as an actual subset of some r to the n with its ordinary subspace topology and verify the manifold axioms from first principles. The strategy is to define the torus as a product of two circles, where each factor already carries explicit projection charts. The simplest piece of the construction is a single circle. The unit circle is the set of points in the plane whose coordinates satisfy x squared plus y squared equals 1, carrying the subspace topology from R2. As the point sweeps around, its coordinates change continuously, but the combination x squared plus y squared stays fixed at 1. S1 is simply the zero set of a single smooth function with no identifications of any kind. A single circle is one-dimensional. To reach a two-dimensional surface, two independent circular parameters are needed. Two independent angles describe every point on the torus, one going around the big loop and one going around the tube. Each angle is a point on its own circle, so the natural parameter space is the product S1 times S1. That gives an explicit map f from the product into R3, the restriction of a polynomial map on R4, so f is certainly continuous. We would like to say much more, that f is a smooth embedding and identifies the product with the donut surface, but we cannot say it yet. Smoothness, immersion, and diffeomorphism all refer to a smooth structure on S1 times S1, and constructing that structure is exactly what the rest of this presentation does. We return to f at the very end, once the atlas is in place. The yellow circle is the longitude. The angle theta sweeps around the central axis, tracing the spine of the torus at radius r. The green circle is the meridian. The angle psi sweeps around the tube cross-section at radius r. Fix theta at 0 and sweep psi from 0 to 2 pi. The red dot traces the full tube circle exactly once, and the spoke connecting the spine point to the tube dot makes this angular dependence visible. As theta varies from 0 to 2 pi, the tube sweeps all the way around the spine circle. Ring by ring, the surface of the torus assembles. Each meridian circle corresponds to a fixed value of theta, and because theta is an angle that runs from 0 to 2 pi, the last ring coincides with the first, closing the surface exactly. This angle parametrization sends every pair of angles to a point on the surface, and every surface point arises from some pair, the pair being unique once each angle is confined to the half-open interval from 0 to 2 pi. The picture motivates the definition, so we now take S1 times S1 itself, sitting inside R4, as our official definition of the torus, the zero set of the smooth map G with the subspace topology inherited from R4. Nothing about the donut surface is assumed here. That identification is a corollary proved at the very end, once the smooth structure exists. One question remains before we can call this a manifold candidate at all. Does this subspace topology on S1 times S1 actually agree with the product topology coming from the two circle factors separately? If they disagreed, the product chart domains wouldn't be open in the torus, and the entire atlas construction would collapse. That is the content of our first lemma. The lemma holds for a simple reason about how Euclidean distance behaves in product spaces. The Pythagorean identity does the work. The squared distance in the combined space splits exactly as a sum of the squared distances in each factor. That identity sandwiches a product of small balls inside a single Euclidean ball, which in turn sits inside a slightly larger product of balls. Squeezing on this sandwich shows the subspace topology and the product topology share a common basis, and a common basis means the topologies coincide. So the torus carries the product topology of two circles. Before building charts, two properties need verification. The torus must be Hausdorff and second countable. Both come essentially for free from sitting inside R4. R4 is a metric space, so given two distinct points of the torus, small Euclidean balls of radius half their distance apart are disjoint, intersecting with the torus separates the 2 points. And R4 has a countable basis of balls with rational centers and radii. Intersecting each of these with the torus yields a countable basis for its subspace topology. Orthogonal projection onto a coordinate axis gives the chart maps on the circle. Take the open upper arc of the circle, where y is positive, and project any point on it straight down onto the x-axis. That projection is the chart map phi 1 plus. As the point moves along the arc, its shadow sweeps across the open interval from -1 to 1, never reaching the endpoints, because y stays strictly positive throughout. The lower arc, where y is negative, gives a second chart by the very same vertical projection. Together, the two recover y as plus or minus the square root of 1 minus x squared. The same construction works horizontally. Projecting onto the y-axis instead of the x-axis yields two more charts, one for each sign of x. The open right arc, where x is positive, projects onto the open interval from -1 to 1 on the I-axis. This is phi 2 plus. As the point moves along the right arc, its shadow on the y-axis covers the interval, again missing both endpoints since x stays strictly positive. The open left arc, where x is negative, gives phi 2 minus by the same horizontal projection. We now have 4 charts in total covering the circle in pairs by vertical and horizontal projection. Two things need checking. Do the 4 arcs cover the whole circle, and is each projection a homeomorphism onto its interval? Both are short arguments. For covering, since x squared plus y squared equals 1, x and y cannot both vanish, so every point falls into one of the 4 charts depending on the signs of x and y. For the homeomorphism property, take phi 1 plus. It is the restriction of the continuous projection onto the x-axis. Its image is the open interval from -1 to 1, and its inverse, built from a square root that never sees 0 on this domain, is continuous. The remaining 3 charts follow by the same argument with the roles of x and y swapped. These 4 charts form the atlas A sub S1, open domains, covering the circle, each a homeomorphism onto an interval. One requirement remains. Whenever 2 charts overlap, switching between their coordinates must be a C-infinity diffeomorphism. Lemma 3 is the key smoothness statement for the circle. First, 2 pairs are automatically disjoint. A point cannot have both a positive and a negative y coordinate at once, and the same sign constraint rules out overlap in the x direction. So only 4 overlaps are non-empty, 1/4 arc of the circle in each open quadrant, exactly as highlighted here. Only these 4 transitions need checking, in both directions. The first transition map is computed explicitly as the point P sweeps along the quarter arc. Drop P vertically onto the x-axis to get the coordinate t, and horizontally onto the y-axis to get s. Both readouts come from the same point on the unit circle, so they satisfy t squared plus s squared equals 1, meaning s equals the square root of 1 minus t squared. On this open interval, 1 minus t squared stays strictly between 0 and 1, so this is a composition of smooth functions. A polynomial followed by a square root away from 0. By the same symmetric argument, the inverse transition is this very same function, so it is a smooth diffeomorphism of the open interval onto itself. The remaining 3 quadrants give the same picture, with signs adjusted for which half of the circle we are on. Each one is again a composition of a polynomial and a square root whose argument stays strictly between 0 and 1, so each transition is smooth with a smooth inverse by the same symmetric argument. Every transition map of A sub S1 is therefore plus or minus the square root of 1 minus t squared, with the sign determined by which quadrant the arc sits in. A sub S1 is a smooth atlas, and the circle with this atlas is a smooth one-dimensional manifold. The torus is two-dimensional. Charts on a one-dimensional manifold become charts on a two-dimensional one by taking products. The construction pairs a chart domain U sub I from the first circle factor with a chart domain U sub j from the second. Their product Vij is an open patch of the torus. Send a pair of points, P on the first circle and Q on the second, to the pair of numbers phi I of P and phi j of Q. That's the map psi ij landing in a rectangle in R squared, the product of the two chart intervals. Since each circle factor has 4 charts, this construction gives 16 charts on the torus in total. Two conditions must hold for these 16 patches to constitute a topological atlas: openness and covering, and the homeomorphism property. Both follow almost immediately from what we already know. For openness and covering, by lemma 1, the product topology on the two circle factors agrees with the subspace topology of the torus, so products of open chart domains are open in the torus, and since the circle charts cover the circle, their products cover the torus. For the homeomorphism property, a map into R squared is continuous exactly when both of its coordinate functions are continuous, and this criterion applies equally to the inverse map, whose image is an open rectangle, the product of two open intervals. The transition map between two overlapping product charts splits into two completely independent pieces. The first output coordinate depends only on U, the second only on V, and each of those one-variable pieces is exactly a transition map of the circle atlas, which lemma 3 already showed is smooth. So, the two-dimensional problem reduces to two copies of the one-dimensional problem we've already solved. So we need one more tool, a fact from multivariable calculus, confirming that smooth in each variable separately, combined into a pair, really does mean smooth as a function of two variables. The reason is short. Take any iterated partial derivative of the first coordinate, f of u. If no derivatives are taken in v, it reduces to an ordinary derivative of f, which exists and is continuous because f is smooth. If even one derivative is taken in v, it vanishes identically, also continuous. The same holds for the second coordinate with u and v swapped. So every iterated partial derivative of f exists and is continuous. F is smooth. Apply that fact directly to our transition maps. Set f to be the first coordinate transition and g to be the second coordinate transition, both smooth on open intervals by lemma 3. The sublemma immediately gives that the full two-variable transition map, built from f and g side by side, is smooth on its domain. Swapping the roles of the two charts gives the identical argument for the inverse transition, so it too is smooth. Every transition map of the product atlas is therefore a smooth diffeomorphism between open subsets of R squared. That is lemma 5. The product atlas on the torus is a smooth atlas. The main theorem assembles every piece of the argument. Hausdorff and second countability followed immediately from defining the torus as a subset of R4. The topological atlas came from lemma 4, 16 product charts covering the torus, each a homeomorphism onto an open rectangle, and the smooth atlas came from lemma 5. Every transition map between those charts is a smooth diffeomorphism. Every clause in the definition of a smooth two-dimensional manifold has been verified directly for this explicit subset of R4, with no quotient and no gluing anywhere in the argument. Only now, with the smooth structure in hand, can the opening picture be justified. F is the restriction of a polynomial map on R4, and in every product chart, the inverse chart map is built from t and the square root of 1 minus t squared, so the composite is smooth. F is injective for a reason that mentions no angles at all. The distance from the image point to the z-axis recovers rho, and rho then recovers all 4 coordinates uniquely. For the immersion property, we differentiate in a chart rather than in angles. The cross product of the two partial derivatives has modulus r rho over sigma tau, which is strictly positive, so the differential has rank 2 at every point. Finally, the torus is closed and bounded in R4, hence compact, and R3 is Hausdorff, so an injective continuous map is automatically a homeomorphism onto its image. F is a smooth embedding and a diffeomorphism from S1 times S1 onto the torus surface. The abstract proof connects back to the torus surface through the embedding F verified earlier, an injective immersion on a compact domain, hence a smooth embedding, sending S1 times S1 onto exactly this surface. Because F is a diffeomorphism onto its image, pulling back any product chart along F gives a chart whose transition maps are compositions of F with smooth maps, hence smooth. So this torus surface itself inherits a smooth atlas. Every property proved abstractly for S1 times S1, Hausdorff, second countable, a smooth two-dimensional manifold, transfers unchanged to the familiar torus in R3. The argument began with the simplest possible object, a circle defined with no identifications at all, just the zero set of a single equation. Two such circles were then multiplied together, and that product, sitting inside R4, became our official definition of the torus. Nothing was borrowed from the donut picture. The first thing we checked was whether the subspace topology on that product agreed with the product topology of the two factors, and it did by a short argument about Euclidean distance. Hausdorff and second countability then followed immediately from the ambient R4. Those properties confirm the torus is a legitimate topological space, but they say nothing about smoothness. For that, charts are required. Building the atlas was the central task. On the circle, 4 projection charts covered everything, and their transition maps are simply the circle equation rearranged, plus or minus the square root of 1 minus t squared. Lifting that atlas to the torus reduces to taking products, and the transition maps split apart into 2 independent copies of the one-dimensional case we had already solved. With 16 charts covering the torus and every transition map smooth, all 3 clauses of the definition are met, and the main theorem follows. Only then did we return to the donut. With the smooth structure finally available, F is a smooth embedding, so the familiar surface in R3 inherits everything proved abstractly. Every clause verified directly on an explicit subset of Euclidean space. That's the torus, built from the ground up.